Okay, guys, so we are on section 7.3, sampling distributions and the central limit theorem. We start off with a slight summary about the section. It says, let x bar be the mean of a simple random sample of size n, drawn from a population with mean mu and standard deviation sigma. Okay, so what we're doing here is we're looking at the sample, information about the sample, and we're taking that from the population. So the mean of the sampling distribution is mu of x bar equals mu. So it's going to actually equal the mean of the population. And the standard deviation of the sampling distribution is going to be sigma x bar equals sigma. So the standard deviation of the population divided by the square root of n. And we know that n is the sample size. Okay, the standard deviation, sigma x bar, is sometimes called the standard error of the mean. So let's look at example 1. Example 1 says a population, so we have two parts here. A population has mean mu equals 6 and standard deviation sigma equals 4. We want to find the mean of x bar and the standard deviation of x bar for samples of size n equals 25. Okay, so I know from the summary above that mu of x bar actually equals mu. So that means mu of x bar is going to equal 6 in this particular problem. Okay, and if I'm going to find the standard deviation of the simple random sample, I know that equals the standard deviation of the population divided by the square root of n. So in this particular case, I know that that standard deviation of the population equals 4. I'll go ahead and write that the mean of that population was also 6. Okay, so that's going to give me 4 divided by the square root of, we know that n equals 25. So that's going to give me 4 over 5, which equals 0.8. Okay. B says a population has a mean mu equals 17 and standard deviation sigma equals 20. We want to find the mean of the random sample, or mu of x bar, and the standard deviation. So sigma x bar for samples of size n equals 100. Okay, so I have n equals 100. I've got my mean of my population is 17, and I have my standard deviation of my population is 20. I know that the mean of my simple random sample is going to equal the same as the mean of my population. So that's going to be 17. And then I can find the standard deviation of my simple random sample by saying the standard deviation of the population divided by the square root of n. So in this particular case, that's going to be 20 divided by the square root of 100. That's going to give me 20 over 10, which equals 2. Okay, this brings us to the central limit theorem. It says let x bar be the mean of a large, n is greater than 30. That does become important. Okay, guys, the n is greater than 30. Simple random sample from a population with mean mu and standard deviation sigma. Then x bar has approximately normal distribution with the two means are going to be equal and the standard deviation is going to be what we just did. Okay, what that's telling you is that you have to have n has to be greater than 30 in order for those things to work out correctly. In order for those means to be approximately equal, that sample size has to be more than 30. Okay, so the procedure for computing probabilities with the central limit theorem is be sure the sample size is greater than 30. Okay, then we can use our normal curve, in which for us, guys, that means we can use the calculator function, the normal CDF, because what you're trying to do is, even though the sample size, the simple random sample initially may not be a normal curve, what they're saying is if you make a population big enough, then it's going to mimic a normal distribution. And you know, in order for us to use those functions on the calculator, like normal CDF, it's got to be a normal distribution. Okay, so be sure the sample size is greater than 30 so that we can use it. We find the mean mu x bar and the standard deviation sigma x bar. We're going to sketch that normal curve and shade in the area to be found. Then we can either find that using a table or technology, and we of course use technology. Okay, when a population is exactly normal, the sample mean will be normally distributed even if n is less than 30. In practice, however, populations are almost never exactly normal. Okay, so let's look at example 2. A population has a mean mu equals 10. And standard deviation sigma equals 8. A sample size (50) is drawn. Okay, we want to find the probability that x bar is greater than 11. Okay, so the first thing we need to do is we need to check n. Okay, so what does n equal here? N equals 50. So I know that n is greater than 30. We get a check mark on that. Then I also need to find the mean of x bar, and then I need to find the standard deviation of that simple random sample. Okay, so I know n is greater than 30 equals 50. It's going to equal the same thing as the mean of my population, which is 10. So that one's pretty easy. Now we need to find that standard deviation. I know that's going to be the standard deviation of the population divided by the square root of n. So that's going to give me 8 over the square root of 50. If we put that in the calculator, go over here, If I clear this, this will give me 8 divided by square root 50. Okay, I'm going to get 1.1314 there. Okay. Now I can find that probability that x bar is greater than 11. So what you're doing, guys, is you've got the normal curve like we had before. This time it says that average is 10, okay? And remember, we didn't have to turn it back into the mean of 0 and a standard deviation of 1. We want to know if 11 is somewhere over here. We want to know this chunk right here. What is the probability that it's going to be greater than 11? We're going to use normal CDF here. Okay, we start with the lower bound, which will be 11. The upper bound we're going to set as 1E99. Then we're going to have the mean, which is 10. And then our standard deviation, which we found to be 1.1314. Okay, so if you need a little refresher there, remember it's normal CDF, it's lower, it's upper, it's our mean, and then it's our standard deviation. Okay, so I'm going to go over here back to my calculator, and remember that is second vars. We're going to pick 2 normal CDF. My lower here is going to be 11. My upper is going to be 1 second, comma. That gives me my E99. I do not have a mean of 0. The mean is 10 here. That standard deviation is 1.1314. I'm going to hit enter, and that gives me 0.1884. So I get equals 0.1884. Okay. Part B asks me, would it be unusual, oops, sorry guys, would it be unusual for x bar to be less than 8? Okay, and I'm not sure if we directly talked about it or not, so I'm going to give you this little blurb right here. If we have under 5% or 0.05, then it is considered unusual. So if there's a 5% probability or a 0.05, if it's under 5% or under 0.05, then it is considered unusual. So what we're going to do here is we do our normal CDF. If I draw my picture, let me draw you guys a little picture. So it's still the same information. Here's 10, my mean. This wants to be less than 8. So let's say, let me make that a little closer together. Let's say maybe down here's 8. Okay. Of course, we have a standard deviation of 1.1314. So it's not quite over 2 standard deviations away. Okay, but it is over 1 standard deviation away. And we want it to be less than 8. So I've got normal CDF. My lower limit is negative 1, E99. I'm going up to 8. I still have a mean of 10, and I have a standard deviation of 1.1314. Okay, so I'm going to go over here back to my calculator. And I'm actually going to retype it. So at second vars, 2. This time I'm -1 second, comma, gives me my E99. I'm going to, what did we say, 8. Standard deviation is still at 1.1314. That mean is still at 10. Sorry about that. Processed a little too quickly there. And I get 0.0385. Okay, so this is 0.0385. So that is less than 5%. It's less than 0.05. So yes, it would be considered unusual to be less than 8 because the probability is less than 0.05. So yes, it would be considered unusual to be less than 8 because the probability is less than 0.05. Okay. Second part of example 2, so it's like there were 2 problems in example 2, both have 2 parts. The second part says a population has mean mu equals 47.5 and standard deviation sigma equals 12.6. A sample size of 112 is drawn. A, find the probability that X bar is between 45 and 48. Okay, so I of course need the mean of that sample, and then I need the standard deviation also. Well, the mean is going to be 47.5 because that is the mean of my population. So that's going to be the mean of my random sample. Of course, I did need to check. I know that n equals 112 here, so it's okay to use my normal CDF and make it mimic a normal curve because it is over 30. My sample size is over 30. And then I can find my standard deviation. So I've got the standard deviation of my population divided by the square root of n. In this particular case, the standard deviation of my population is 12.6. So I've got 12.6 divided by the square root of 112. So if I go over here and I say 12.6 divided by square root of 112 is going to give me 1.1906. 1.1906. Guys, you do have to calculate those two so that now we can use our normal CDF function. And like I said, we can use that normal CDF function because we do have a sample size that is over 30. Okay, so we want between 45 and 48. So lower limit's 45, upper limit's 48. I have a mean of 47.5 and a standard deviation of 1.1906. So if I go back, I'm just going to clear this. I'm going to say second vars. I'm going to say 2. I'm going between 45 and 48. I have a mean of 47.5 and a standard deviation of 1.1906. Okay, and that should give me 0.6449. 0.6449. Okay, that is the probability. There's about a 64% chance that you're going to get a value between 45 and 48. Okay. B says, would it be unusual for X bar to be greater than 48? Okay, so we're looking if we get a probability of over or under 0.05, then yes, it will be unusual. So I'm going to do my normal CDF here. It says greater than 48, so my lower limit is 48. My upper limit is 1E99. My average is 47.5. And then I need, my standard deviation is 1.1906. And when I put that in to normal CDF, I'm going to go up here. Let's see if I can just edit this one. I'm going to do 48. Whoops, sorry guys. This is going to be 1 second E 99 comma 47.5 comma 1.1906, and I get a 0.3373. So 0.3373. Guys, that's a 33%. That's well over 5%. So not unusual, because it is greater than 0.05. And that sums up 7.3 for us for the week.